Good evening, Dr. Osbey. This is my video for the project submission, project 1 about the converging diverging nozzle geometry. I will now show you all of my work. Okay, so these, actually don't need this guy. This row is my conical nozzle geometry. This row is my 70% bell nozzle geometry. And this one was just a test one that I don't need anymore. So we're going to go through just to show you. Great. This is the geometry that I came up with. The cross section can be seen here in my file. You'll see this on the submission menu. These are all of the dimensions, and I rotated it and created a 3D model. I did not finish 3D analysis, so please just create the 2D portion of it at this time. But what did I do here? So after my calculations, in my calculations, you'll see when I submit them, but I calculated the throat diameter as well as the exit diameter, and the optimal length of the nozzle. And the other values are arbitrary that I did to try to fit the nozzle and make it look somewhat realistic. And this box here is just to analyze the fluid flow after the nozzle. That's what became of the cylinder here. So that takes care of the geometry section. Afterwards, I needed to mesh it. All right, so 2 seconds. The computer was not really built for this, but it's okay. Did manage to make it all run. And it's just loading. Being modified, so smart. Okay, that's fine. Okay, so this is the meshing portion. If I click on my mesh here, you can see. Let's see what steps I do here. I changed the preference to CFD as I had to conduct computational fluid dynamics. I changed the element size to better fit my nozzle, and the last step I did was inflation to better approximate how fluid would flow along the curves of the nozzle here. That's why you can see the mesh, it sort of created like rectangular geometry like right next to the wall. And I just took like this is how it would look at a 3D portion, but I took a cross section in order to ensure that the inside of the mesh was good as well. So that takes care of that. I will go to the solutions for this. All right, fantastic. So I had to approximate the inlet as an inlet. These 3 faces had to be approximated as walls because I did not want any fluid flow out of the nozzle to turn back on itself and go backwards. And then I called it the flame plume is this step here. It basically acted as an outlet where I could analyze the parameters that you asked for after they flowed out of the nozzle. The plots that I made are as follows. We have velocity contour to see how it changed with velocity. I ran this for, I should talk about that first. I ran this for 100 iterations because my computer was struggling a little bit with running more than that. So 100 iterations. Additionally, so to set this whole thing up, I had to create an energy balance. I changed it to the viscous behavior to what's called K epsilon. According to tutorials that I saw, this would best approximate fluid flow within a closed system like this, like especially supersonic flow, so that's what I used. After that, I had to check the... Oh, I changed it to ideal gas behavior. If we go into here, I can show you that. Yeah, I had to set the behavior of the gas to ideal, and I had to set the molecular weight to 20, as was stated in the problem. What else? I had to change the parameters. I had to change the inlet to a pressure inlet and apply the given pressure that was stated in the problem statement, 9.7 e to the 6, I believe. Oh, that's I had to account for the atmospheric pressure as well, so I increased it to 9,801,000, as well as the temperature of the chamber I had to set there. I did the same for the outlet, except for the outlet I just set the outlet temperature because there was no pressure. I ran it as if it was running an atmospheric, because I have not done the bonus ideal over or under expanded cases. After that, then I ran it with 100 iterations and created the contours. So this is the velocity contour. We have a pressure contour. We have a density contour, speed of sound, temperature, and Mach number. And for the plots, we have the same parameters: velocity, pressure, density, speed of sound, temperature, and Mach number. And that takes care of the conical nozzle. So after the conical nozzle, what came the 70% bell nozzle? Very similar, but I realized after my previous analysis that my analysis area, the cylinder, should have been a little bit larger to allow me to get a fuller picture, so I expanded it out quite a bit. I can show you here that I went from 0.75 by 5 to 1.25 by 15. I kept the throat diameter and the exit diameter the same. The rest were, again, arbitrary to make it appear realistic and behave realistically. And besides that, it was all the same. The mesh parameters were all the same. I will show you my simulation data, though, if we can get into there. I did the same sort of steps: activate the energy balance, K epsilon behavior of the gas, setting the boundary conditions. All of that was exactly the same as the previous example. The only thing that we changed was the geometry. So I go into the contours. That is strange. Where are my contours? I'm not sure where my contours went. I might have clicked on the wrong simulation. This might be my test one. So instead I will show you them on my Word doc that I will also submit to you. These were all the ones that I showed you of the conical. These are of the bell nozzle. You can see it's a little bit larger. So that was velocity, pressure, density, speed of sound, temperature, and Mach number. Then these were the plots I already showed you. Now we go to the plots of the bell nozzle, which is velocity, pressure, density, same order as last time, and that is my data. And that's how I conducted this project. It was actually a great experience, and I look forward to doing a lot more CFD in the future. It was a great experience. Thank you very much.